Welcome to this multiscale multimodal digital rock analysis presentation done by Gwenole Talek. With a background as a software engineer, Gwenole Talek is now a digital rock analysis expert at Thermo Fisher Scientific. Gwenole is dedicated to supporting customers and helping them move to digital software solutions in order to accelerate their daily research work. Here is the outline of the presentation: data presentation and experiment objectives, segmentation and upscaling, upscaling workflow, analysis. I now give the floor to Gwenole.
Using PerGeos Software for your digital rock analysis gives you confidence in your results. Its multiscale, multimodal workflow helps you validate observations and properties from a variety of datasets. Here you can see the source of the data we will analyze using the multiscale, multimodal workflow. A 7.5 cm tall, 38 mm wide plug taken from a carbonate rock sample from the Middle Eastern region. So, what do we hope to achieve with this experiment? First, we want to validate the segmentation and porosity upscaling workflow. With this workflow validated, we can then apply it to other samples. Second, we want to validate the segmentation of the small scales in order to conduct flow experiments. Our digital rock analysis workflow is a typical multiscale, multimodal image analysis workflow. It involves analysis of the plug, extraction of a subplug and its analysis, and cutting of the subplug for thin section analysis. The porosity of the plug has been measured at 14.4% in the laboratory. The full multiscale span ranges from 1 mm whole core CT to 1 nanometer FIB-SEM. Looking at this full multiscale picture, we will focus here on the three primary modalities: one acquisition of the plug with a 16 micron resolution microCT scan, one acquisition of a subplug with a 5 micron resolution microCT scan, and one acquisition of a thin section with an SEM at 2 microns. This is the carbonate rock plug scanned at 16 micron with a Thermo Scientific HeliScan microCT. Looking at the images, it is obvious that some pores are not resolved. Therein lies the challenge of this analysis. We will try to resolve this plug at smaller scales and upscale the results. Performing a direct segmentation of the pore space highlights the inherent limitations. The porosity is 11%, whereas we know from the laboratory measurement that it should be 14.4%. This means that important parts of the images contain unresolved porosity. We have chosen to go deeper in resolution until the discrepancy in pore space is resolved. Let's have a look to the subplug scanned at 5 microns. The data is composed of 3,892 slices with a size of 30 gigabytes. Segmenting the pore space with a direct method gave us about 11% for the porosity. There still remains some unresolved pores, forcing us to look at smaller scales involving electron microscopy images. A thin section has been extracted and acquired with an SEM at a 2 micron resolution. We can visually assume that the pore space is resolved. The pore space has been segmented with a direct method. Now, the porosity value of the slice has been computed to be 10.56%. Now, let's have a look to our upscaling workflow. We will first need to register the SEM slice with the 5 micron subplug, as you can see in this short video. Once registration is completed, we can easily extract the exact same slice from the microCT subplug. Reporting the pore space of the slice, we highlight that the direct porosity segmentation of the 5 micron plug is missing small pores. We can infer this because the value of 7.7% is far from the actual porosity value of 10.56%. Upscaling is done with the adaptive thresholding module. As we have the same exact slice at two different resolutions, we can input the 10.56% porosity value obtained from the SEM on the microCT slice. We then obtain an absolute threshold value that we can report on the entire subplug with a global thresholding. With this method, we assume that the missing porosity is lying in the lowest intensity regions. This is quite logical since microporous regions globally have a lower intensity than rocky ones. As we had obtained 14.41% for the connected porosity, the porosity result is encouraging. In order to upscale the subplug porosity to the larger plug, we apply the same method. 3D to 3D registration, adaptive thresholding with the input value of 14.95%, global thresholding with the obtained intensity value. The new pore space on the entire plug is giving a porosity of 15.2% with a connected porosity of 14.6%, which is completely in line with the measured lab value of 14.4%. The following video will show how this is obtained in PerGeos software. This is highlighting the 3D to 3D registration, where the subplug must match the larger plug exactly, even if they don't have the same resolution. Now that the pore space has been upscaled, we will conduct permeability experiments. The absolute permeability will be computed using three different methods: finite volume, Lattice-Boltzmann, and pore network model. The relative permeability will be computed using pore network models. The analysis workflow involves the research of an REV. In order to do so, we start with a 400 cube that is progressively extended to a 2000 cube in order to look for a convergence of the results. This graph shows the absolute permeability results of the subplug at 5 micron. As this is an heterogeneous sample, we have increased the convergence criteria, thus computation time is important. Note that by using the Lattice-Boltzmann method, this could be accelerated by increasing the number of computation nodes. This graph shows the porosity values and equivalence between the same volumes, but at different resolutions. Obviously, porosity discrepancies decreases as volume size increases. This graph shows the porosity absolute permeability cross-plot results of the 16 micron plug. Lattice-Boltzmann and finite volume are close in terms of resulting values, whereas pore network model, due to the small volumes, contains discrepancies. Finally, what we show here is the relative permeability curves for primary drainage computed with our pore network model-based solver. The purpose for superimposing the curves is to look for a convergence in order to establish a size for the representative elementary volume. We can assume that the volume should be at least 800 cube in order to reach a convergence. This animation shows the three different samples, all registered, and the segmented pore space. You can see the progressive upscaling from the SEM slice to the larger plug. I would like to point out that other alternatives to this upscaling workflow exist. The alternatives consist of differentiating the micropores from the macropores. Such a differentiation is done during segmentation with either machine learning or deep learning. It may even be done with direct methods involving watershed transforms. Then, a multiscale pore network model is generated, and the simulations are conducted separately at every scale before being merged back with an upscaling process. This work is being conducted by our experts, and we will soon be communicating more about this topic. Note that segmentation by machine learning and deep learning is already available in PerGeos software.